So, hello everyone. It's our great pleasure to have Professor Robert McRae from BIMSA to give the talk today. His topic is about his recent work on commutative algebras in braided monoidal categories and rigidity. Let's welcome.
Okay, thank you. Thank you, Elon, for the invitation to give a talk and the introduction. So, yeah, mainly my talk is pretty categorical. But I do want to start with a talk about what my motivation for looking at this was. So I'm interested in representation theory of vertex operator algebras. So probably I should start by saying a little bit about what motivated me to start looking at these kinds of uh, commutative algebras in monoidal categories. So, so my goal is to understand representation theory of vertex operator algebras using basically tensor categorical techniques. If you're not familiar with vertex operator algebras, it's not really a terribly important part of my talk, maybe, but just to say a few things that they are an algebraic method for studying 2D chiral conformal quantum field theories. And if you know about conformal field theories, you probably know of them as a source of modular tensor categories. And indeed, there's a theorem by Ija Huang, which says that if you have a vertex operator algebra that is particularly nice in some way, so strongly rational seems to be the words people are using these days, then you do get a semi-simple modular tensor category. Rational VOAs more or less correspond to rational conformal field theory. And I'll also mention this conjecture that maybe a number of people have made, but I think in particular people like Terry Gannon these days are making this conjecture that maybe every modular tensor category it comes from a rational VOA, or maybe if you're mainly interested in unitary tensor categories, you want to look for unitary VOAs, or if you prefer analysis more, you could look for completely rational conformal nets. So this is sort of the one of the nicest parts of this theory of VOAs is this theorem that you get modular tensor categories. However, VOAs are usually not rational. So practically, that means they have representation theory that's not finite or not semi-simple or both. And in this more general setting, there's a general theory of Huang, Lepowsky, and Zhang, which gives a construction of braided monoidal categories coming from VOAs. But I should say that it's not so easy in general to check that if you're given a category of modules for a VOA, whether it satisfies the conditions of this general theory that you need for this monoidal category construction to work. But the good thing is there are a lot of non-trivial examples that are now known. I've listed a few of these. They're C2 cofinite VOAs, which are essentially as good as rational VOAs, except that their representation theory is not semi-simple necessarily. There are VOAs from affine Lie algebras. These correspond to WZW models in conformal field theory, or in mathematics, Kaja and Lustig also studied these tensor categories and show that they are equivalent to quantum group categories, at least in many situations. There are VOAs coming from the Virasoro algebra. This includes some rational ones, minimal model, central charges, but not all of these Virasoro VOAs are rational. There are many other examples you can build, maybe using some standard constructions, like taking particularly nice subalgebras, or taking extension algebras, or tensor products of VOAs. There are various things you can do. But this general construction just gives you a braided monoidal category. It doesn't really give some other nice properties that we like to have, such as rigidity especially. So one of the biggest questions that we have with these VOA tensor categories is we don't know if they are rigid or not in general. Um, so maybe this is contrast with the situation for Hopf algebras, like if you think of tensor categories coming from finite dimensional modules of a quantum group, then essentially rigidity is built into this structure because you have an antipode. But as part of the data of a Hopf algebra, but there's nothing like this for VOAs. So it's not so easy to show whether we have a rigid category. And in fact, many of the categories we look at here are not rigid. You can think of a VOA as being some kind of generalization of a commutative algebra, and um, you can certainly create braided monoidal categories from modules for commutative algebras, but you don't always get rigidity. Another question that I like to address is whether these categories are actually semi-simple. Sometimes if maybe you start with a rational VOA and you do one of these kinds of nice constructions, like taking a nice subalgebra or an extended algebra, you might like to know whether that VOA is still rational. In particular, has semi-simple representation theory. So these kinds of rigidity and semi-simplicity problems are kind of what I want to look at. Um, so I want to start talking about uh, extension algebras. Um, so um, so one thing we can do if we want to show rigidity is we can try to relate the VOA that we have to some VOA that we know about where we know rigidity. For example, if you start with a vertex operator algebra, you can look for subalgebras, you can look for extension algebras, and try to relate rigidity for V modules to rigidity for the larger extended algebra A. So I want to consider this general situation just where we have an inclusion of vertex operator algebras. And I want to assume that we are given a braided monoidal category of V modules, which I will call C. And then I want to assume that this algebra A, considered as a module for V, is an object of this category C. So we can start using techniques from tensor categories in this situation because of this theorem of Huang, Krylov, and Lepowsky, which says that A has a structure of a commutative algebra in this braided monoidal category C. So that's so maybe I should review what is a commutative algebra in just quickly go over the definition of a commutative algebra in a braided tensor category, a braided monoidal category. So it's an object A of the category. There's a multiplication morphism, which is a morphism from A, tensor A to A. And then there's a unit morphism, which is going from the unit of your tensor category to A. And then you have an associativity for this multiplication. And you have commutativity, because you have a braiding in your category, you can write down this commutativity property that you can, I guess this is a typo. This should be an A tensor A in the upper right corner. So the commutativity takes you from A tensor A to A tensor A, and then you multiply. Should be the same as just multiplying. There's also a left unit property, and because we have commutativity, there's also a right unit property of this multiplication. And I'll just quickly mention that in this VOA context that I'm interested in, this multiplication morphism is induced by this vertex operator, which is essentially the main part of the data for this VOA structure on this algebra A. So that's a commutative algebra. And then we can also do representation theory for commutative algebras and braided monoidal categories. So I want to use CA for the category of modules for the commutative algebra, because we have a braided monoidal category and a commutative algebra. It's good enough for me to consider just left, or I could consider either left modules or right modules, and I prefer to have the algebra acting on the left side. So a module in this category comes with an action of A on M. So isomorphism from A tensor M to M. And then there's a diagram for the associativity of this module action, and then also a unit property for this module action. I guess there's another typo here. This should be yeah, this should have been an A tensor M, and this should have been an M, I think. So, but anyway, these are the two properties of a module action. And then because we have a symmetric, we don't have a symmetric braiding in this category, which means that if I look at the commutativity isomorphism for the module M and the algebra A is not necessarily the same as its inverse. So if I start with a left module, I can define a right module structure on M in two different ways, one using the braiding and one using the inverse braiding. And I want to say that a module is local if the two right module structures that you define in these two different ways are actually the same. So composing the multiplication with the braiding is the same as composing the multiplication with the inverse braiding. So that would be a subcategory of CA. And then, so just under some very mild assumptions, like we assume C contains coequalizers and the monoidal product preserves coequalizers, so it's good enough to assume that C is an abelian category and the tensor product is right exact. Then you can get a monoidal category structure on CA. The tensor product of two objects is given by a coequalizer of two morphisms. So you have two ways that you could have A act on M1 tensor M2. You could have A act on M1, or you could use the braiding to move A over M1 and then have A act on M2. And you want the tensor product in CA to be the quotient that makes these two actions equal to each other. So that gives CA the structure of a monoidal category, and then CA local is a braided monoidal category because the braiding on C induces a braiding on CA local. And then there's one more theorem that we have that connects this general category theory setting to the VOA setting that was my original motivation for this. So if you have this setting where you have a vertex operator algebra V and a braided monoidal category C of V modules, and then A is a vertex operator algebra extension of V that lives in this category, then this CA local braided monoidal category is isomorphic to the vertex algebraic braided monoidal category of A modules that you would get just by considering certain objects of C as A modules. So this is, I believe, this original paper of Huang, Kirillov, and Lepowsky showed that this category CA loc is isomorphic to the category of A modules, where you consider A as a VOA. And then with Thomas Creutzig and Shashank Kannada, I proved that the braided monoidal structures also correspond under this isomorphism of categories. So essentially, you can completely translate a lot of questions about VOAs to just general questions about commutative algebras and braided monoidal categories. And the main problems I want to think about in this talk are the rigidity and semi-simplicity problems. So if C is rigid, then what about CA local? Is that also rigid? Or if C is semi-simple, is CA local semi-simple? And then maybe the converse and harder direction is if CA local is rigid or semi-simple, then what about C? Is C also rigid or semi-simple? Or under what conditions could that be true? So just to give an example of one kind of result you can get in this direction, there is a theorem of Kirillov and Ostrik, which says essentially that if A is a separable commutative algebra, let's say in a rigid, semi-simple, braided tensor category, then both of these categories, CA and CA local, are also rigid and semi-simple. And in particular, if you want to think about how do you take the dual of an object of CA, well, you just have to give a natural A module structure on the dual object in C. And that gives you a dual in CA. And separable means, just to be precise about this, separable means that if you look at this multiplication, A tensor A to A, this is a morphism of A bimodules. And separable just means that this A bimodule surjection splits. And for example, if you have a ribbon category, then the algebra will be separable if the dimension of A in C is non-zero, plus maybe some minor other conditions, like maybe you want to assume A is simple and that the twist of the ribbon twist acts trivially on A, something like that maybe. But essentially, this dimension should be non-zero. And unfortunately, this non-zero dimension condition isn't so easy if your category C isn't so nice. So, if C is unitary, then, for example, then these dimensions are all positive real numbers, so there's no issue with dimension equaling zero. Or if C is pseudo-unitary more generally, but when we look at rational VOAs, most of the tensor categories we find aren't unitary or even pseudo-unitary. So this is a bit of a problem for us if you want to go outside of the unitary modular tensor category setting. So the first result I want to talk about uses this idea of, instead of looking at separable algebras, let's instead look at exact algebras. So the definition of exact algebra. So an algebra is exact. Let's say we have an abelian monoidal category where we can talk about projective objects, for example. So the algebra is exact if for every module M in CA and every projective object in C. So you can get a new module by tensoring M with P on the right. So since I want A to act on the left, I want to tensor P on the right, and I get a new object of CA, and that object should be projective in CA. So if this object in CA is always projective, whenever P is projective in C, then I say that an algebra A is exact. And maybe the reason why you want to call this an exact algebra is this result of Etingof and Ostrik, which says that if C is a finite tensor category, so in particular we're assuming rigidity here, then if A is exact, then any C module functor from CA to any other right C module category is exact. So I haven't really defined what a C module category or a C module functor is, but at least this gives some idea that an exact algebra tells you something about exactness of some natural kinds of functors. So why are exact algebras good for the rigidity problem? Well, it turns out that if you have an exact, let's say, commutative haploid algebra in a braided finite tensor category, so I think I didn't say what haploid means. It's just minor condition to say that there's only one-dimensional space of morphisms from the unit object to A. But anyway, if you have such an exact algebra in a braided finite tensor category, then CA and CA loc are both rigid. And what I want to point out here is that in general, the dual of an object in CA is not necessarily going to be given by an A module structure on M star. So how do you prove such a result as this? Well, the basic idea is that you want to think about the category of A bimodules. You want to identify A bimodules with the category of C module endofunctors of C. So this is a category of functors where the monoidal product is functor composition, and duals are given by left and right adjoint functors. So that is going to be equivalent to the category of A bimodules in this exact algebra setting. And then you can embed CA into the category of A bimodules by using the braiding to give any left A module a right A module structure. And then you show that that CA embeds as a monoidal subcategory that's closed under duals. So it's a subcategory of a rigid subcategory, which is closed under duals, so it's a rigid category. But it's not so easy to see what the dual of any object is because the duals are coming from, well, just the abstract existence of adjoint functors in this functor category. You cannot be so explicit maybe about what this dual object looks like. So that's a good start to this rigidity problem, but we need to know how can we tell whether an algebra is exact. Unfortunately, there's a very nice result of Etingof and Ostrik, which says that if you have an indecomposable algebra in a finite tensor category, then it's going to be exact if and only if A is simple, and this funny sort of tensor product of the left and right duals of A tensored over A, this should be a non-zero object. So this actually, you don't really need A to be commutative in this case, and you don't need C to be braided. In that case, this A star is going to be a right A module naturally, and star A is a left A module naturally, so you can tensor them over A to get an object in C, and this object of C should be non-zero if you want to have an exact algebra. I should mention that the proof of this is a very nice proof, but it heavily uses Frobenius-Perron dimensions, so unfortunately it doesn't seem easy to generalize to non-finite tensor categories. But if you're mainly interested in finite tensor categories, and this is a great theorem to have, for example, you can easily see that if A is commutative and simple, and there exists a non-zero morphism from A to the unit object, then the algebra will be exact, and therefore CA and CA loc will be rigid. So in this case, the existence of this non-zero homomorphism from A to 1 helps you define a right A module isomorphism between A and A star. So then this funny tensor product of the left and right duals just amounts to star A, which is also isomorphic to A. So that's non-zero. So then you get that this algebra exact and these categories are rigid. Another very nice corollary of this is that if A is commutative and simple and you assume that C is semi-simple, so we're assuming now that C is a fusion category, then CA and CA loc are also going to be fusion categories. So this of course in a semi-simple category you have a unit isomorphism from 1 to A, so that means semi-simplicity tells you you have a non-zero morphism going back from A to 1. So that means you get the rigidity and of these categories and the exactness. So you get the rigidity, and then you also want CA and CA loc to be semi-simple. And that's easy because the definition of exact algebra is simply that if you take any object of your module of your CA category and you tensor it with a projective object of C, then you get a projective object in CA. So in a semi-simple category, the unit is projective, so that tells us that every M is projective in CA. So that means CA is semi-simple. So that's a really nice theorem that tells you if you want to get new fusion categories from commutative algebras, it's enough just to find a simple commutative algebra in a braided fusion category. Okay, and then let me say a little bit about VOA applications of all this. So, this last corollary about fusion categories that I gave essentially immediately gives you this nice VOA theorem that says that whenever you have a simple n-graded, integer-graded VOA that contains a strongly rational vertex operator subalgebra, I think I have a typo here. I said then V is strongly rational. Actually, I meant to say that A is strongly rational here. So yeah, what this theorem is saying is that if a simple VOA contains a strongly rational subalgebra, then it is also strongly rational. And in particular, representations of this strongly rational VOA are going to be a modular tensor category. So this is nice again because usually these rational VOAs are not the module categories are not unitary in general. So this dimension condition that I was mentioning earlier is not always obvious. But it turns out we don't need this dimension condition to show that extensions of rational VOAs are rational. We also have results for non-rational VOAs if you want to forget about the semi-simplicity. So then you get this notion of strongly finite VOA, which satisfies essentially all the properties of rational VOA, except you don't assume semi-simplicity. And several groups of people have conjectured that if V is a strongly finite VOA, then its representation category should be a non-semi-simple modular tensor category. That means it should be a finite braided ribbon category, such that the braiding is non-degenerate. So it's everything that a modular tensor category is, except you don't require semi-simplicity. So this is still a conjecture, unfortunately, but a lot of partial progress is known. So it's known that if you have a strongly finite VOA, then rep V, the category of representations, the full category of all representations, is a finite abelian category. It's also a braided monoidal category with a ribbon twist. And a few years ago, I proved that if this category is rigid, then its braiding is also non-degenerate. So the only question left is whether rep V is rigid, and that seems to be a very difficult question in general. But at least we now have this theorem which says that rigidity is preserved under taking extensions, at least under some minor technical condition here about this funny tensor product again. So if A is a simple VOA that contains a strongly finite subalgebra, and now this A prime here is the so-called contragradient module of A. So this is A prime is it would be both the left and the right dual of A considered as an object, considered as a V module. It also has an A module structure. So we again want this tensor category to be non-zero in order to get this algebra A to be exact. And if A is exact, then its representation category will be rigid. So we get a non-degenerate braided finite tensor category. The only thing is whether the ribbon structure on the category of V modules extends to a ribbon structure on the category of A modules. And that will be the case if A is isomorphic to its contragradient A prime as a V module, and also if we assume that A is n-graded. So that if we assume that A is simple, n-graded, self-contragradient, so A is isomorphic to A prime, and it contains a strongly finite subalgebra, this means A is itself going to be strongly finite, and its representation category is a possibly non-semi-simple modular tensor category. So these are the main VOA applications of this theory of exact algebras and braided tensor categories. So for the second half of the talk, I want to consider the converse question. So now suppose we have a commutative algebra in a braided monoidal category C, and let's assume that CA local is rigid. So it's a rigid braided monoidal category. So what can we say about C? Can we get some conditions that guarantee that C is also going to be rigid? So to figure out what kind of conditions we need, there are a couple problems that we need to solve. Maybe the first problem is that we need there to be some way to get rigidity information about CA from the rigidity of this subcategory CA local. And the main reason for this is that we want to use the monoidal functor of induction, which I call F, going from C to CA, sends X to A tensor X with this multiplication. And in general, if you start with an object X and you induce it to an object, you get an object of CA, you don't usually get an object of CA loc. So, you'd like the fact that this is a monoidal functor to tell you something about rigidity of C, given that CA local is rigid, but first you need to get rigidity for CA if you want to do something with this. So that's the first problem. And the second problem, which maybe I will talk about first on the next slide, is that we need some kind of weaker duality structure to get us started with rigidity in C. So we need some kind of weak duality structure that at least gives us candidates for dual objects in C. And the solution to the second problem is what has recently been called Grothendieck-Verdier category structure. I suppose that this name should come from Grothendieck-Verdier duality. I don't know too much about that, but anyway, it's something that's very natural if you're interested in VOAs because, as I mentioned on the previous slide, there's this notion of contragradient modules for VOAs. And there's a recent observation of Allen, Lentner, Schweigert, and Wood. It says basically that if you have a VOA tensor category that has contragradient modules, then contragradient modules give you a Grothendieck-Verdier duality structure on this category. So let me say, what is a Grothendieck-Verdier category? So let's just start with C being any monoidal category. So we call an object K and C dualizing if, well, essentially if this functor Halm C of blank tensor X going into K is representable, that means there exists an object dx such that there's a natural isomorphism between these two Halm functors. And besides this natural isomorphism, we want to assume that this D here defines an anti-equivalence of the category. So this natural isomorphism tells you how D should be defined on objects, and you can easily define D on morphisms as well. Gives you a contravariant functor, and you want this contravariant functor to be an equivalence. So that's what a dualizing object is. And then a Grothendieck-Verdier category is just a monoidal category that is equipped with a dualizing object. And a braided Grothendieck-Verdier category is just a braided monoidal category with a dualizing object. And then you also have this notion of ribbon Grothendieck-Verdier category. That means you want to have a twist. Natural isomorphism of the identity functor satisfies the usual balancing equation for twists and ribbon categories. And we also want it to be compatible with this duality functor D in the sense that theta of dx is d theta x for every object. And there's this nice observation of Boyarchenko and Drinfeld. So I think Boyarchenko and Drinfeld, I should say, are responsible for calling such categories Grothendieck-Verdier categories. So I think this was about 10, 15 years ago. They published a paper on this. And one of the nice results in their paper is essentially a classification of dualizing objects in a category. So if you have any two different possibly dualizing objects in a category, which would give you two different functors d1 and d2, then there exists an invertible object in the category such that k2 is J tensored with k1. And conversely, if K1 is a dualizing object and J is invertible, then J tensor K1 is another dualizing object. So it tells you that dualizing objects are a torsor over the, I guess, what would you say, the Picard group of the category or something like that, the group of invertible objects in the category. So what that indicates is that if you have is that Grothendieck-Verdier duality is a structure on the category. It's not a property like rigidity. If you have a rigid category, then every object just has one left dual and has just one right dual. But you could have multiple Grothendieck-Verdier structures on a category coming from different dualizing objects. And that's quite important for what I will be discussing on the next few slides. So just to emphasize, why is Grothendieck-Verdier duality a weaker version of duality? Well, if you have any rigid monoidal category, then it automatically has a Grothendieck-Verdier structure where the dualizing object is the unit object and the dualizing functor is well, this I guess I would usually call this the left dual functor. Maybe some people call it the right dual functor, but is whichever duality functor you need to get this natural isomorphism here to hold. Um, Conversely, if you have a Grothendieck-Verdier category, then there is a way to get some kind of evaluation morphism, uh, which I call EX, going from DX, tensor X, going to the dualizing object K, and it's the one that corresponds to the identity of DX under this natural isomorphism here. So you get some kind of evaluation, but it goes to the dualizing object, it doesn't go to the unit object necessarily, unless K is equal to 1. So what we want is to start with a Grothendieck-Verdier category, and we want to show that it's rigid somehow. So that means it's probably best that we start with a Grothendieck-Verdier category where the dualizing object is 1. And Boyarchenko-Drinfeld called such a category an R category. I'm not sure why they use that terminology, but that's convenient enough to use. So here's the basic theorem about commutative algebras in Grothendieck-Verdier categories. So we want to assume that we have a braided Grothendieck-Verdier category, and A is a commutative algebra, and C. Ultimately, our goal is to find conditions such that if CA local is rigid, then C is also rigid. So that means later we want C to be an R category where K is 1 because that's what we need to get rigidity. But we don't really need this assumption for the first theorem. So the first theorem says that if C is a braided Grothendieck-Verdier category, is a commutative algebra, maybe you should assume a few other things like like the C should be closed under coequalizers and the tensor product should preserve coequalizers, that kind of thing. Well, in that case, CA is also a Grothendieck-Verdier category. And the dualizing object is an A module structure on the Grothendieck-Verdier dual of this object A. And then we would also like CA loc to be a Grothendieck-Verdier category, but it seems a bit difficult to show that this is true in general. So, but in general, we do have this condition that if C is a ribbon category, ribbon Grothendieck-Verdier category, such that the twist on A squares the identity, then CA loc is a braided Grothendieck-Verdier category, and with the same dualizing object. So the point of this condition here is it allows us to show that this object dA is still a local module. In general, dA is an object of CA, and it's not so clear whether it's a local object, it's an object of CA loc. But this condition on the ribbon twist tells us that dA is an object of CA loc. So it's a dualizing object of CA loc. And then if we want the ribbon structure on C to give us a ribbon structure on CA loc, then we should assume that theta A is actually equal to the identity of A. So that's the basic theorem. It's fairly straightforward to prove, just a lot of things.
Finiteness condition, right?
Sorry?
You don't need any finiteness condition in this theorem.
Yeah, there's no finite. No, this is completely general. Yeah.
Okay, so if I
Yeah, I think the only condition you need is this coequalizer condition so that at least C is a monoidal category.
okay,
Other
and
than that's
also
completely general.
if I twist the the K by a invertible object, then this data it won't change this statement, right? So if I
Yeah. So of course, yes, if you change by an invertible object, then yeah, that will change. Yeah, so if you change the dualizing object of C by an invertible object, that will change the dualizing object of dA.
okay,
Um, but yeah, I guess it should. Well, yeah, it could mess up the this
that's what
statement
I
about
was
CA loc
yeah,
because the old ribbon twist might not be
yeah,
compatible with the new dualizing object of
yeah,
C.
yeah,
The
yeah.
theta might not give you a ribbon structure on C with the new dualizing object.
Yes, yes. Okay, okay. Thank you.
Right. Yeah. Okay. Yeah, so this is a very general statement. Okay, so now I want to say something about getting rigidity of CA. So if we want, so let's see, we have a ribbon R category. Let's say C is a ribbon R category now. So the dualizing object is 1. A is a commutative algebra which satisfies these conditions to guarantee that CA loc is a Grothendieck-Verdier category. And let's assume in addition that CA loc is rigid. So what I want to point out here is that this means that CA loc has two Grothendieck-Verdier duality structures. One of them comes from the Grothendieck-Verdier duality structure on C, just as in this previous theorem. And the other one is the rigidity structure, because we're assuming this is rigid, and rigid categories are Grothendieck-Verdier categories as well. So this is we have potentially two different dualizing objects. One is dA and the other is A itself. And they may not be the same. But this result of Boryachenko-Drinfeld tells us that there is an invertible object such that A is the tensor product of J and dA, which tells us that dA is an invertible object in CA loc. And of course, it's also going to be invertible in CA. And the inverse of this of dA is going to be J, of course. And then again, we can tensor any dualizing object with any invertible object to get a new dualizing object. So we think of dA as a dualizing object of CA. We tensor it with its inverse, and we get A, which is a dual, and so A is going to be a dualizing object of CA. So this tells us the R category structure on CA loc, this rigid structure on CA loc extends to an R category structure on all of CA, but that doesn't tell us whether CA is rigid yet. So if I want to show that CA is rigid, it would be nice if I could reduce it to the case of rigidity for simple objects. And indeed, there's a nice argument by induction on length you can use that shows that, let's say you have a locally finite abelian R category where all the simple objects are rigid, then all the extensions of simple objects are also going to be rigid, and every object is finite length, so then every object in the category is going to be rigid. So then, based on everything so far, if I assume that C is locally finite abelian, and I assume that every simple object of CA is local, and yeah, I guess I'm still assuming that CA local is rigid, then CA is also going to be a rigid category. And this may seem like a little bit of a cheating way of getting rigidity of CA because I'm making this strange assumption that every simple object of CA is local. That's maybe a little bit of a strange assumption that's definitely not going to be true in many situations. One situation you might be familiar with is, so here I think about it in VOA terms where I have a vertex operator algebra, and I have an finite automorphism group, and I look at the fixed points under this automorphism group. Or if you want to think about this more categorically, that means you start with a category C, which contains a copy of rep G, and then you do this de-equivariantization, and you get an algebra object A. And so you can consider CA, which will be a braided G-crossed monoidal category. So this category in general will contain simple G-twisted modules in the twisted sectors of CA, if you prefer to call them. And these kinds of twisted A modules are not local. So this is a situation where most simple objects, the CA category, are definitely not going to be local objects. So why is it useful to have this kind of result where I make such a strange assumption? Well, actually, in non-semi-simple settings, there are many examples where of algebras A, where every simple A module is local, even in non-symmetric settings. So when you study VOAs with non-semi-simple representation theory, a lot of the time you construct them using some kind of what's called a free field realization. Maybe a good example of this, maybe I should start with the example of this the so-called singlet algebra, which is labeled by an integer greater than or equal to 2. This is a vertex operator algebra, which is a subalgebra of a rank 1 Heisenberg VOA, or another way of putting that is a free boson, one free boson VOA. So this VOA H is well known to be a nice unitary VOA with semi-simple representation theory with central charge 1. However, you can deform the conformal structure. This is what Fagan and Fuchs did. And they found a Virasoro module structure on H of any central charge. And here I'm fixing an integer p, and I want the central charge to be this central charge 1 minus 6 p minus 1 squared over p. So I view H as a module for the Virasoro algebra with this central charge. And then there is some sort of screening operator that you define on this, and which is some linear map from H to some module for H. And then this singlet VOA M of P is the kernel of the screening operator. Another way of thinking about it is when you view H as a module for the Virasoro of the central charge, it's not semi-simple for the Virasoro anymore. And M of P is going to be the Virasoro Sokol of this non-semi-simple Virasoro module. So this is a situation where it turns out that H is an indecomposable module for M of P. Another example is, which I want to talk about at the end of my talk, is this affine VOA of SL2 at fractional levels, positive rational fractional levels. It's called admissible levels. This simple affine VOA, which is not rational, it embeds into the tensor product of a rational Virasoro VOA with some kind of free field type of algebra, which in this case is what's called a half-lattice VOA. So this is sometimes called the inverse Drinfeld-Sokolov reduction, because if you're familiar with Drinfeld-Sokolov reduction, what you do is there you start with an affine VOA, you tensor it with a free field algebra, and then you get a W algebra as some sort of cohomology of this tensor product VOA. So this is kind of the inverse, where you start with a rational W algebra. Virasoro is the W algebra for SL2. You tensor with a free field algebra, and then you get the affine VOA out of that in some way. In this case, just as a subalgebra of some sort. So these are examples of the situation I want to consider, because this Heisenberg free boson algebra H has nice rigid semi-simple representation theory, has a pointed category of representations. And then the Virasoro VOA has a modular tensor category, and this pi 0 has a pointed tensor category. So you tensor them together, you still get a nice rigid semi-simple representation category. So we want to exploit this rigidity somehow to get rigidity for example, this module category of this simple affine VOA, for example. Okay, so now I need to set up the main rigidity theorem that I want to discuss here. So let's say we have a commutative algebra, locally finite abelian ribbon R category with all of these conditions that we had before. CA local should be rigid. I want to assume every simple object is local. Well, in this setting, as I discussed earlier, this means that CA is rigid, and then its Drinfeld center is also still going to be a rigid category. And we can lift the induction to a braided tensor functor f prime going from C to the Drinfeld center of CA. And the idea is we want to show that this f prime is an embedding. We want to show that C is actually a subcategory of this rigid category. If it's a subcategory of rigid category, then it will itself be rigid, at least as long as it's closed under duals. So we want f prime to be an embedding, and we want it to send the Grothendieck-Verdier duals in C to the rigid duals in the Drinfeld center of CA. So that's enough to show that C is rigid. About this condition of whether it sends duals to duals, well, the Grothendieck-Verdier duality, you can use it very easily to find a natural transformation from f prime of dx going to f prime of x dual. But it's not so obvious in general whether this is an isomorphism. So we will in general need to do some work in order to show that this actually is an isomorphism. And then also to show that f prime is embedding, that is fully faithful, we also need some sort of mild non-degeneracy condition on C, which I will state precisely in this theorem here. This is the main theorem that we have in our paper. So we have all these assumptions about C. We assume CA local is rigid and every simple object is a local module. That tells us that CA is rigid. And then I have, this condition 2 is just some sort of minimal condition that I need to get the f prime functor to send duals to duals. So it's enough to show that if I look at this morphism between the ordinary induction functor and duals in CA, then it's an isomorphism. And then this third condition is this mild non-degeneracy condition I mentioned. So essentially, for any non-trivial subobject of A, you want to show there's some object that's not in the Muger centralizer of this non-trivial subobject that also satisfies this injectivity condition. So it's just some technical assumption that we have to assume. So under all of these conditions, C is going to be a rigid category because it will embed into the Drinfeld center of CA, which is rigid. And so finally, I just want to go over what is our main application of this result so far. So this is for the weight modules of the affine Lie algebra of SL2 at these so-called admissible levels, which are these fractional level. So these have been, I guess, for maybe quite a long time, maybe 20 years or so, this has sort of been one of the key examples that people really wanted to understand for doing in logarithmic conformal field theory as opposed to rational conformal field theory. So you know that when you have an affine Lie algebra at a positive integer level, you get a rational VOA and a modular tensor category. Well, if you start looking at fractional levels, it's natural to consider the same kinds of VOAs and ask whether you get some nice tensor category or not. So it turns out that if you want a good category for doing conformal field theory, you have to look at this very large category of weight modules. So weight modules are modules for the affine Lie algebra that have a double grading. They have a double grading by generalized eigenvalues of the Virasoro operator and also eigenvalues of the Cartan subalgebra generator H for SL2. So they should be doubly graded. So in rational conformal field theory, the conformal weight spaces are finite dimensional. Here, these Virasoro L0 eigenspaces are not finite dimensional, but if you fix a lambda, then the doubly homogeneous space is finite dimensional. Also, in rational conformal field theory, the L0 eigenvalues of any module have a lower bound. In this case, we can have arbitrarily negative conformal weights, but if we fix a lambda, then the doubly homogeneous space is equal to 0 for sufficiently negative conformal weights. So it's sort of these sort of local finite dimensionality and lower bounded conditions. So this is a very large category because it includes a lot of modules that have these kinds of big L0 eigenspaces. And it was maybe just in last year in a couple of papers that Arakawa, Creutzig, Kawasetsu, and then in a second paper by Thomas Creutzig last year, they showed that this category of weight modules is a locally finite abelian R category, like the assumptions in the theorem over here. And if you're interested, it also has enough projective objects, so it's a pretty nice category. Pretty nice as an abelian category. It's also a monoidal category, but then the question is whether it is rigid. Yeah, and then, well, as I mentioned, we do have a commutative algebra in this category, obtained from a rational Virasoro VOA and this free field type algebra. And as a module as an object of this category, this algebra is indecomposable, contains the unit object, which is just the simple affine VOA, as a sub-object, and then it contains some simple quotient, which is not isomorphic to 1. So when you dualize, this turns the exact sequence around and you get a different object. Another nice feature of this category is that for any simple object in the category, embeds into a unique simple object of CA loc. So that's quite important for the theorem that we proved that this category is rigid. So I should mention that there are actually 2 proofs of rigidity for this category that were posted on arXiv on Monday. The first one is by Nakano, Rose, Hunziker, Rose Camacho, and Wood. They used a heavily analytic method. They did some explicit analysis of some correlation functions and were able to prove rigidity in this way. And then in the other proof by Thomas Creutzig and Jinwei Yang and myself, what we did was we checked the conditions of our main rigidity theorem, starting with rigidity for CA local and then getting rigidity for C. So first step, there are 4 steps to the argument. First, we compute the induced module, f of A, as an object of CA. This requires just calculating one non-trivial fusion rule in the category C. That's the only fusion rule that we need. Second step is to use this to show that every simple object is local. So the idea there is that if we have any simple object in CA, say X, then it's a finite length object of C, so it contains a simple C submodule Z. And that gives us a morphism from the induced module to X. So we kind of want to see what this induced module looks like, get some information about this induced module to see what possible simple quotients it has. There's a very nice relationship that says that if you look at the induction of any object of CA loc, then as an object of C, you can write it as some kind of tensor product in CA. And we already computed what f of A was. We know what the fusion rules in CA loc are because they're very easy. So this gives us a lot of information that allows us to prove that any simple quotient of f of z has to be local. Maybe I won't say anything too much more about that. Step 3 is we finally compute all of the induced modules explicitly, and that allows us to do this check that any morphism from this this induction functor commutes with the dualities. And just as an interesting byproduct of this, we can actually completely, at least in terms of the category structure, we can completely describe what the projective objects in the non-local module CA look like, because CA loc is semi-simple, it turns out, but you can take non-semi-simple extensions of objects in CA loc, which turn out to be non-local modules. And then there's this mild non-degeneracy condition that I mentioned earlier, and that's pretty easy because we can show that CA local is non-degenerate, and then we have this property that any simple object of C embeds into a simple object of CA loc. So we think that this general strategy could apply to a lot of non-semi-simple braided tensor categories that come from VOAs that have these kinds of free field realizations or inverse quantum Drinfeld-Sokolov reductions. These results that we have are also could be useful results in the direction of proving that these braided tensor categories are equivalent to quantum group categories. So we're hoping that there will be quite a few applications of these ideas, and that's all for my talk. So thank you.
Thanks, Robert, for the great talk. Let me see. There's a question. Is it proved for strongly finite VOAs that their tensor categories are GV or ribbon R categories?
Yeah.